Welcome back to Cloud Computing and Big Data. Today we have our lecture 1 on cloud computing and big data as an introduction. So we will basically go into a few more details we have learned during the prologue of this course, and here and there have some real insights from real cloud vendors, but also some lessons learned over the years to really give you a 10,000 feet perspective of cloud computing and big data, what the role of services mean, why big data is not only volume, but also velocity and veracity and many other challenges alongside it. But before we dive into the material of lecture 1, let us just review what we had the last time. And we looked in practical lecture 0.1 really as an introductory topic again into Python and Jupyter. So these two words are incredibly important, especially in the data science track of university. So if you want to be a data scientist in the future, you have to make sure that Python and Jupyter is something you really know by heart. And hence, of course, we could not introduce Python as a whole course here. Just this was an overview lecture. And I know that some lecturers in the university here already teach Python. And Jupyter has a very good idea also to understand a little bit remote versus local execution. But for data science, no matter where you go, which cloud you actually face, and if it's the Amazon Web Services, Microsoft Azure, or Google Cloud, or whatever, Python is really something which is everywhere deployed, everywhere available, and there are lots of different interesting data science packages today. Just to remember ourselves what data science really means, you could see it's a blend of data mining, of machine learning, and also applied statistics. And you could add much more, like signal processing, for example. But one of the unique selling propositions that this data science term in a way carries is also one of the emphases on computing. So here we think about more large scale in this course, but of course data science as such can be also small scale, where you can still execute it on a laptop, on a small device, maybe a workstation is one GPU. But here in this particular course on cloud computing and big data, we really want to scale up. We want to see where computing faces limits, where your laptop has maybe memory limits, where basically the CPU is not, fast enough to process all the data, because the data is such as big as we know from the prologue. And with this, we look a little bit into the cloud here. There's other paradigms which are basically high performance computing, another course I teach here at the university. But this particular course looks now more into remote execution in forms of services that are offered by many different cloud providers. You see here these famous three with Amazon, Microsoft, Azure, Google. But there's UberCloud, there's lots of different cloud vendors we will learn and understand throughout this course. And the last time we're looking into basically how we can leverage Python for data science. And one of the examples we had, apart from the very basics we had with vectors, matrices using NumPy and things like that, we also looked a little bit at a data processing example or pre-processing example where we think, okay, there's a character recognition idea. There are some handwritten characters, which is a real problem. And we want to understand if a machine can be trained, if a machine can be learned, that makes it machine learning. Basically, later on, a machinery that can actually automatically understand from an image of handwritten characters, what exactly is this character showing? So it's a 0, a 4, a 1, like we humans do. But of course, we want to automate the process. And the machine should implement such a process. We didn't go that far and didn't implement machine learning yet, but of course we take the baby steps before that, which is very important in the crisp DM process I showed you last time. And this usually starts with the business understanding, data understanding, and data exploration, data basically pre-processing to make it then really in a way ready for machine learning. And that's what we did with Python last time. And we have seen the libraries of Python are just beautiful. To do that, we actually explored how basically these images really look like 28 by 28 pixels, maybe as one image here. And then we have seen the 0 here, or the 4 and the 1 would be somehow a grayscale in some sort of fashion. So identifying then the real character. And by this, we could print out a little bit very easily the data set that we had, that we differentiate between training and testing. Things you don't know, obviously, right now, but which will materialize in lecture 2, lecture 3 throughout the course. However, we keep the machine learning here to a moderate degree. As I said you earlier, if you want to really learn machine learning by heart, much more with statistical learning theory and more details which are necessary, you have to take also another course called machine learning here at the university or somewhere else. However, the second part then of this course last time was really understanding not only that Python is important and Python is powerful with all its different libraries. We have seen it also with MLX10 for the shopping data we analyzed. More importantly, also, we looked into Jupyter. And we use the Anaconda toolset on your local laptop to understand, okay, we have a very local execution with that. We have a local host set up that you see mostly in the browser where things running. And the difference between a remote execution inside the cloud or on a high performance computing is basically already differentiable often by using just the URI. So we have seen the example last time of using the Jupyter JC that you will also use in your assignments. By identifying that this is not anymore localhost, you go beyond the boundary of the localhost laptop, right? And with this, you have a remote execution. And this is incredibly important for cloud computing, which I also will reveal today. And this could be all sorts of services. We used a very, let's say, trivial service with a Jupyter notebook in the sense of having just this Jupyter that you already had in Anaconda locally, now remote in the cloud. And we used it here for this character, recognition data set and analyzed it and looked at it. And basically we have seen it looks and feels as it is in your local browser, very local as you have seen it before or with Anaconda, but in fact, it's executed remotely. And you will see that Amazon, Microsoft, and Google, and they all, the big players, have all somehow a Jupyter Lab remotely accessible because it's one of the big tools in data science today. But let us come also now to more details. Let us come to the first introductory lecture, which really gives you cloud computing more comprehensively than the prologue could really do. From another perspective, I would say like a 10,000 feet perspective, understanding the term services, understanding why basically cloud computing has such an uptake. And here and there, we'll really give detailed examples of existing cloud vendor services that we have in Amazon, Microsoft, or so on. So the outline of today is really understanding the foundations of cloud computing. So obviously it has some evolution from parallel and distributed computing, perhaps partly even from high performance computing. And the internet is of course key to this. So it's a remote execution of services that you want to access with your local laptop, maybe even with your handheld device, with an iPad, iPhone, etc. And this means we need internet, we need distributed computing again, and we will see a little bit on this, how this kind of terminology then came into play to really create cloud computing, which is a relatively new term compared to parallel and distributed computing that has been way longer existing, or high performance computing. Cloud computing is really a business term coined in the last 20 years more and more to really make the services, make the business footprint into parallel and distributed computing with so-called services that we have to learn. But of course, with this alongside was also the technology advances. The internet is much more faster. We can do this remotely, right? We couldn't do that maybe 20 years ago. And also the parallel computing advanced. Not only do we have lots of multi-core GPUs, we also these days have many core GPUs that basically you should learn as a technology foundation today. And of course, as I was saying, one of the key terms in cloud computing today is really service, or more broadly speaking, as a service. Something as a service is really an approach that we will learn throughout this course. And I give you here and there some examples. In the second part then of this course today, we will look a little bit more on big data. Of course, the course is called Cloud Computing and Big Data, so we have to see both facets, which actually play nicely along. So we will understand a bit more what big data is, what the key challenges is behind the term, because it's not only always volume, as I was alluding to in the prologue, it might be also velocity, 1 petabyte per 20 seconds, for instance. Then we will look into the idea of if you have big data problems, why we don't solve that with memory, right? Because memory is very very fast, it's beautiful, we can use it, it's super, but in the end, it's very limited. It's very limited size, it's very costly, so we have to go to disks, and even if you go to a, let's say, storage hierarchy, as we would call it, you even have to consider that petabytes and petabytes again and again, at some point in time, probably have to go to more tape archives, which are even slower. So here we have a problem we have to elude, basically in all the different use cases over the course, but we will also talk about this a little bit today to see that there's a key problem nowadays of really accessing all that data, of this big data, fast enough to fuel, so to speak, data into the CPUs and GPUs at speed. For this, we also have to change the view a little bit today, which means we don't only look on compute, as it is always a little bit the focus. Here we also have to think about examples of cloud storages. So what happens to all the petabytes? Maybe in the future we have exabytes, right? Not anymore petabytes. The next generation is actually talking about exabytes. So this is a kind of problem we will see as a so-called scalability approach. We look into also if you think about Facebook accumulating a lot of data, like YouTube, like all the social, networking sites, they accumulate a lot of data, and this means they require a lot of scalability inherently, which we'll look briefly into it. Of course, the whole lecture today will be linking to different lectures all over the course. We will not learn everything around cloud computing and big data today. Rather, it's an orientation for you from a 10,000 feet perspective to see where are the topics in the course, where are the challenges that this course, try to tackle to give you some, really tools at hand that you can maybe leverage in your business once you graduate from here or in your SME and so on, or that you can actually also use to solve some interesting research questions, which brings us a little bit to one of the big ideas how actually big data can be used. It is called big data analytics, and we will contradict this a little bit with big data analysis versus also cutting edge machine and deep learning models we can do these days in cloud computing. So an interesting comprehensive lecture giving you in one way a whole overview of the course, and we will start a little bit with the foundations of cloud computing right now. So you would see, of course, your question is, what is cloud computing now, and how is it different from HPC? How it's different from typical distributed systems, services, networking, I know, a little bit of hardware, I know, with big systems. The idea is basically you put that cloud term, which stands for elasticity. We will also learn in one of the later lectures, but a key term that always comes into play is that it's basically a service-oriented cloud here of virtualized resources or software that you have inside, which you pay for. So, and this paid services that you pay for are usually the key foundation why actually there are so many cloud vendors today, because you actually have to pay for what you use. They're different, basically usage models, paid by subscription, paid per use. We will also review that basically all over the course. But the key idea is that basically you have this magic cloud, if you want, from a 10,000 feet perspective, abstracting away all the complicated manners that you would have maybe, for instance, in high performance computing to just log in via SSH, to call Jupyter yourself, to do basically there are some installations of packages. So the vision that cloud computing has is just more being user-friendly. You swipe your credit card, you pay for it, and you basically can now submit your request as a user, whatever it is. You want to use Jupyter, you want to store your MP3 collection or your photos into the cloud. And the one key term is really the service around it. So it's made easy. There's a simple upload service maybe existing in the cloud already for your pictures. If you know a little bit about Instagram, for instance, that might be one of it. So these are the ideas. Make it simple for the people, for the users to use these services. And of course, usually by paid services, let's say Dropbox for storage, right? You want to store your MP3 collection, your videos, your photos you take with your iPhone, and you want to store it, but you want to do it basically by using a Dropbox service. So you pay for the service, get good, let's say, reliability, get good fault tolerance. There would be probably a duplication or basically kind of replication idea behind these photos. So you can always think like when this cloud or your laptop is disappearing, the good idea is that all your data, so to speak, is in the cloud. Needless to say that this is, of course, a security point, right? Do you really want to have all your data in the cloud? Of course, in a way, the internet clouds are always saying, okay, it's perfectly secure, nobody can look at it, it's perfectly secured, etc. But we have also seen with Garmin watches and others that, of course, these services also can be hacked, and then basically maybe your user data is then free in the cloud. Or free in the internet available. And of course, this raises security concerns where this has something to do with medical records that you may not want to really put in the cloud. Although, of course, it's nice, right? You can change between different devices. You could see I have my handheld device now or my laptop. I can always access my health situation online. But then you also have to trust, of course, and trust is a strong word in cloud computing to really make it safe and sound. But in a way, that's the 10,000 feet perspective that you have here. It's fueled by virtualization. Hence, we will talk in lecture 4 much more about virtualization as a key enabling technology. We put that aside for a couple of lectures just to make your assignment 1 faster, right? So that we can hand that out faster. Then we will review in lecture 4 again, the virtualization technology. So the evolution of cloud computing, though, is something which really was coined many decades ago. So with parallel and distributed computing, which is really the foundation of cloud computing inherently. There was no talking about big services at that time. There was no infrastructure as a service, software as a service 30 years ago. But the key idea of doing it with high performance computing or with high throughput computing was already there and already used in different applications. And at that time, of course, it was already big data at that time because the computers have been not really powerful as today. So let's say in that area, megabytes, maybe even terabytes were a big challenge, while we today, of course, consider rather exabytes as a challenge. So these parallel computers have been more and more used and more users have been exposed to it. It was very complicated in the last 30 years, so to speak, to always use some of these technologies, rapidly advancing, always changes. But over the time, the idea of really this cloud computing was embarking out of it and was saying we have to make it simpler for users, right? If they want to pay for it, that's what we have to do. And basically, this really was the feedback you get in all of this complicated technology that was around in 30 years. And although basically you would say that there are different ways of how to do computing in the cloud, which were 2 paradigms that always will exist. And one of it is here, this high performance computing, which is easily recognized by the fact that all the different nodes, all the computing has a very high interconnect bandwidth, or it's a very fast network connections between all these different node and HPC machines. So that makes it a little bit homogeneous in a sense. But the interconnect is really important. In HTC, it's more for farming jobs. So the interconnect is actually not that important. You break down the problem in a very few pieces, and then you let them independently work on it or nicely parallel work on it. And at the end, you're just interested in the result. So this course here, in the cloud computing course, is much more here and there oriented towards HTC, although you find HPC resources in all the big cloud vendors today. But still, they're not really in the, let's say, high orders number of cores or numbers of GPUs. It's rather smaller numbers of GPUs and cores that you find as HPC services in the clouds, not what we have in Jülich or not what we will strive for in the Euro HPC ecosystem towards exascale performance. However, HTC has a certain selling proposition. And of course, this is really, if the jobs on these different nodes don't have to communicate a lot, right? Then this is just beautiful. You can use it. And that's what basically cloud computing also entails. Many of those service offerings entails access to high throughput computing. And that's what we will focus on in contrast to the HPC course. So what are these paradigms we can use? Another evolution over time to really see that these systems are paradigms that have been developed in parallel together, that in a sense, based on their modus operandi, on their nature, will be always existing because it's so different. It has been through many different areas. It has been to P2P networks, then coming to computational data grids, while basically H performance systems were always about cluster computing, large, let's say, massive parallel programs, or basically processor systems, always basically this big kind of systems that basically all of them united a little bit in this computation great data grids idea. We called that a little bit grid computing, which then basically was an evolution again towards the Web 2.0 services, the internet cloud computing that you see today, and the Internet of Things, perhaps, that we're still evolving today. Everything has an IP address, even your toaster maybe, giving you and delivering you data. However, you see also for Internet clouds here, virtualization is a key term. So we will talk about it in lecture 4 and the relevance also for Internet clouds. And if you ask yourself today, do you know cloud systems? I'm sure you know, you will definitively say yes. So when you use Google Docs, you're effectively using already Google, basically cloud services. When you are on Facebook, it's another type of a cloud. Amazon Web Services, a bit more special. It's not the Amazon shopping page, what I mean here. It's more really services for the cloud. We will look into several examples of them, but this is what you do. You essentially already use today very many of these examples. And in the course, we will basically tackle many of them and we'll talk many of them throughout the course, like the Uber Cloud, for instance, a very specific niche market in a cloud for engineers of having different services. Or the European Open Science Cloud that you see here a little bit, where Iceland is involved in the Nordic fraction, which has very specialized services in the cloud for researchers. So just to capture a few things we say here in terminologies which really matter. So centralized computing is really the idea of thinking about that is all in one physical system, right? So which means there's one big system, but in the end, the point today is it's basically also limited to have such a system. So you rather would go to a modular systems that we have see right now here, where parts of it is a cluster module, maybe with high single thread performance CPUs, where parts of this is an extreme scale booster with many, many cores to scale up and boost up your scaling really with these accelerators. And you have specific modules, maybe with high memory for doing in-memory computing with data analytics, or basically also parallel file systems to enable large storages, which are then connected maybe to tertiary storage and tapes. So in a way, that's kind of this evolution of centralized computing, which is much more moving towards a modular supercomputing approach. So inherent, a system which is also more modular. And the parallel computing idea is really that you always think like one processor at a time. What you see here is doing something in parallel to the others. Let it be I/O here in the big data course where you want to dump big data, and every processor is somehow involved in order to do that and have its own computation, its own result dumped to disk then basically. This is just one idea. We call that shared memory parallel programming or distributed memory parallel programming. The course on HPC, which is complementary to this, talks about this much more than the cloud course. But in the cloud computing, also parallel computing matters with parallel programs, parallel programming ideas as well. Then distributed computing is really where, let's say, it fuels much more cloud computing. You have really an idea of distributed systems. You have a mesh, so to speak, around the world, which is essentially the internet, and then connecting every single device around the globe to this kind of idea of building and forming this interesting cloud where you can find all the different services. And in this sense, it's distributed, going beyond the organizational boundaries that we have. And with this also needs to be, specific messages from one end to the other end. And of course, specific programs and services that enables us to think about distributed computing. And we will learn about this, like, for instance, MapReduce as a paradigm for this distributed systems. We will talk in this course. And in this sense, there will be lots of early examples of cloud-like examples, even for research. You see here the BOINC infrastructure, the Berkeley Open Infrastructure for Network Computing, was one of the very first that had the idea of this distributed computing really understood by everyone could at home, contribute to a project called SETI at home. Today we have Rosetta at home, for example, also basically to see about medicine and other interesting ideas. And here the idea is really that everybody contributes with its own computing device. Ordinary desktop computers, very much around the world could fuel and help in different problems which have been, centralized, organized, but basically executed, then distributed among all your laptops, which give, let's say, free cycles to this BOINC infrastructure. So we called that scavenging at that time, to use really unused resources, maybe on your laptop, on clusters which are basically almost to be shut off. Now, in the energy crisis, you would say today in Europe, this kind of unused resources are something of history. So we rather shut off the cluster if we have something like this. But at the end, the idea of these services, of the distributed computing approach, was already there, especially in the light of the fact that it's really geographically distributed computing, right? And this is something where this BOINC infrastructure was very famous for a long time. Now, another interesting example today, still relevant, is this modern infrastructure as a service. We talk about infrastructure as a service a lot in the course. And here you can see one famous example of the Amazon EC2. EC2 stands for Elastic Compute Cloud, and this elastic paradigm already should give you an indicator why clouds are so successful. It enables you to do elastic load balancing, which means that basically we can scale up, scale down these EC2 devices that you see here. So as a company, you have some certain demands which are maybe relatively constant, but there's some point in the year where you have maybe some peaks, let's say Christmas shopping times for a retail shop, but also could be tax, calculations for a normal organization in some certain month. So the beauty of these clouds is you can scale up and scale down the amount of many core GPUs or multi-core CPUs that you have. And you see, basically, they are very flexible mechanism in the cloud, and that's why the cloud paradigm came into play. Clouds sometimes are large, they grow, they shrink. Basically, here it's according to the demand. And many people use it exactly like this. And for example, the New York Times is one example here. And it has lots of different resources and services available that you can combine with these kind of lowest level computing if you want. You can combine it with different, Amazon Web Services, cloud storages, S3, to basically augment the computing, also the storage. It's a relatively safe way of storing data as well. It's already, let's say, quite good protected, not so easy to hack. And we will talk about this infrastructure as a service model much more in detail than in lecture 8. But we talked about CPUs and GPUs, and some of you have attended my HPC course, I know, so you know the difference already, but some here in the cloud computing course maybe not. So what's the difference between these CPUs and GPUs? So the multi-core CPUs is something that you see a little bit pointed here. You have different cores, really the one that do the execution with different level of caches here. That actually is your memory to fuel these kind of computing entities with data. And these cores all have in common that they have a very high single thread, so that you could see the thread performance. So basically you would say the heartbeat is very fast. The trouble you go into with the heartbeat, so to speak, is very fast of these cores is that the chip, because they're all on one chip, is getting very hot. And with this, you get bit errors and all of these different, let's say, aspects you don't want to have. Hence, we're kind of limited of creating more and more multi-core processors, because the sheer fact that it's getting more and more heat on the chip is preventing us from having error-free chips, or they basically fail quickly. So this is some of the biggest problems we had at some point in time, that essentially we cannot get better chips. We cannot have better multi-core chips. But the solution that, today has really made a strong impact in the field since then was, why not using thousands of cores, but with a moderate thread performance? So here, the heartbeat of these processors that you have here of all these different cores is actually not a very high single thread performance. Instead, it's rather moderate or low, and they don't have really level of caches. They have just a device memory, and that makes it a sort of accelerator for certain problems. That's what we see the GPU today. So obviously it came from the graphics. So I think some of you know a GPU was always very good for gamers and for graphics processing. And what people have now tried is to use the GPU successfully for general purpose computing with a GPU that makes it a GP in front of it. And this actually works quite well for massively parallel problems that you have, that basically all of them, all the computations you may have are not that challenging. So you don't need a single thread performance core. It may be just simple multiplications, simple additions, but you just do hell a lot of them. Like speaking of thousands on a core on a GPU device today. In contrast, of course, to the multi-core you just have seen, where the cores are very limited because they're so fast. So this gives us the key ingredients from the hardware perspective of clouds. And to fulfill a little bit the next layer as a idea how can use a cloud also as your own. I would say the Google Cloud is a good example here to show you another facet. We have talked about infrastructure as a service, which is incredibly important. You need still some computing entities. You need something where you store your storage. But of course, a cloud can be also much more. In a way, you would say the platform as a service is the next level on top of it. And of course, we speak in lecture 9 much more about it. It's oriented towards developers. I like to have the analogy of this Lego service bricks, right? So if you want to play, or basically if you want to create a game like, Angry Birds or something else, or the Philips Hue system for lighting, you are interested in many different aspects, but not only computing and storage. You need a billing system, you need a proper user interface. You want to, have different versions somehow because you develop this kind of app any further and further. So you have a complete life cycle of developments to actually track as a kind of cloud developer, right? And the Google Cloud is just one example with the Google App Engine, for instance, how you can nicely do this. And basically have lots of Lego bricks, which you otherwise have to redevelop yourself, already readily available, right? And this means you can create your app these days in the cloud as simple as possible. So you just have lots of different services already available. So, and we will look into this, of course, into the course, how people have used and leveraged these Lego bricks basically in all these different clouds then in order to create games, or basically with Philips Hue as an example. Also, we talk also about Warcraft at some point in time. So the Rovio games example is, of course, a quite interesting one if you think it was, again, absolutely not taking off. And the interesting thing is today, that Angry Birds, they have movies, they have successful apps, you have, branches, you have Star Wars apps on Angry Birds, Rio, whatever different facet you have. So extremely successful, but it wasn't always like that. So they had to scale up with their users. They started very small and suddenly it was a big boom. They really had to go and grow fast, really, with their users. You see here some numbers, 140 million downloads and users. So you have to have an infrastructure in computing and storage that really can support all of that, which is not so easy to create. And hence we will learn basically in our lectures later why basically this approach from Angry Birds was based on clouds, how they scale up using different parts of the Google Cloud Platform, for instance, that are just beautiful to show that the scaling again, right, on a different level. Now we just not talking just about computing and storage, it's about the user management, the session management, and all of that. Then basically to fulfill the layered hierarchy, we would say there's infrastructure as a service. On top, you might say there's platform as a service, and as a top layer, you would say there's software as a service. So software as a service is the one where you basically swipe your credit card and you have no basically contact anymore, so to speak, with the underlying infrastructure. You don't even know basically that it's existing. So you have a fully fledged software, which is available, which of course builds on top of IAAS services, PAAS services somewhere, but it's so nicely, let's say, created for you that you as a user, you just swipe the credit card to the subscription and you go with it. Here I put you one example called the Amazon SageMaker for machine learning and deep learning, where you can train models, basically very nicely scale out to distributed training inside the cloud. You see also here as a good example, create notebook instance. Of course, here you have a Jupyter notebook that you can start in your Amazon SageMaker. As I was alluding to earlier, the Jupyter notebooks are everywhere in the clouds, And here, of course, you have to pay for the service, but it's a very powerful service. There's a integrated development environment really for machine learning. It tracks all your different services that actually executes machine learning models. We will talk about this more in lecture 2 and 3. You don't know exactly how that materializes right now, but in a way you want to tune your model later where you get help at hand and then deploy this model for inference or once it's trained to be really used. And this is, a lots of time consuming manual installation if you usually want to do it yourself. All the deep learning frameworks, machine learning programs, and they'll have to match the right Python version, etc., and let alone this nice, graphical user interface to track all the runs, the performance you have in accuracy and so on. So I'm not paid by Amazon. I just say it's a beautiful service, but of course, here you go, right? You have to swipe your credit card and the services are basically, of course, not free. So you need to have a subscription, and that's where the cloud business model starts. With a subscription, you get often a free test period of a couple of weeks or months, and then, your credit card is charged. And we will talk about this much more in this course again and again, how this, of course, fuels also the market of clouds. And I think the first part of this lecture, we have given you hopefully a very good overview of cloud computing, and this kind of interesting, rather simple video will explain again the key message, which is the remote execution, again, the distributed computing approach I want to convey with this video.
So you're at your computer working on some important files. Suddenly, a meteorite bursts through the window and flattens the computer. But as you stare into the crater, you smile and think, at least my photos, music, and important documents are stored online in the cloud. When something is stored in the cloud, that means it's saved on internet servers instead of on your computer. It's like having an extra hard drive you can access anytime you're connected to the internet. You can access your files anywhere by using cloud-based apps. Some run inside your computer's web browser. These are called web apps. And some of them can also be installed on your mobile device. For instance, Google Docs is a cloud-based app that you may already use. It's free, and it allows you to view, create, and edit many types of projects. You can access Google Docs from almost any device with an internet connection. Since you only need a connected device to access the cloud, you can take your files wherever you like. You can take a photo on your smartphone and upload it to a cloud-based photo storage service like Google Photos or Dropbox. Then you can access that photo on any of your other devices like your computer or TV. You can even work on a document when you're far away from your desk and share it with anyone you want, instantly. Storing files in the cloud is a great way to protect them from accidents, viruses, and more. You can use cloud-based storage services like iDrive or Backblaze to back up the contents of your computer. These services run continually and back up automatically. This way, you will always have the most recent versions of your files stored in secure online servers. If something bad happens to your device, you can easily transfer your backup files from the cloud to another device. Whether you're backing up photos and music that you love, or using a file on the go, the cloud has a lot to offer. Plus, when your files are stored in the cloud, you won't need to worry about losing them to a computer malfunction or a rogue meteorite.
GCF Global, creating opportunities for a better life.
All right, I think that's all what we have here on the table for you in the first part of the course. We break here for 10 minutes and see you in the second part of the course, ours today.